Hello, this is Dr. A.J. Kumar, PhD. So, a couple days ago I did a video where I went over this problem, basically showing algebraically how to solve 6x plus 7y equals 2, 3x plus 2y equals minus 4. And our goal with this was to find the numbers x and y such that both of these equations are true. And I want to give you some taste of what the geometry is that's going on here. So I'm going to open a program called Geogebra. Okay. And what I'm going to do is I'm going to first plot the equation, the first equation. 6x plus 7y is equal to 2. Okay, that's a line. And I'm going to I'm going to give it a color, and I'm going to color it red. Okay. And then the second equation is 3x plus 2y is equal to minus 4. Okay. And I'm going to color this one, actually, I'm going to color this one blue. That's a decent enough color. It's kind of an ugly color scheme, but oh well. So, if you think about it for a second, it should be obvious. So, each one of these equations describes a line, and what was I going to say? Each of these equations describes a line, and the point, and so what we're asking is the numbers x and y such that both equations are true. Well, if you think about it, that is asking for what are the coordinates of the point which is on both of these lines. And when we go all the way down to the bottom, we got that, okay, I'm going to write this. X is equal to minus 16 times 2 ninths, or minus 32 ninths. Ah, that's a vertical line. And y is equal to 10 over 3. There's the horizontal line. So, geometrically, what this Gaussian elimination does is gradually change this system of two lines. I'm going to take these crosshair lines and make them dotted lines, just so that we can see what's going on. Dotted lines. Okay. So all that Gaussian elimination does is takes this system of linear equations and converts it into this crosshair system, this one where it's x is equal to something and y is equal to something. And if you were to plot, each of these intermediate steps, I tried that in a previous take and it got kind of messy, so I'm not going to do that, but I encourage you to get Geogebra and do this by yourself. Then what you get is sort of a set of intermediate lines that sort of converge to this one, to converge to the crosshair system. Now, I mentioned that because the determinant is not equal to 0, that it actually doesn't matter what points or what values are over on the right-hand side of this equation, so 2 and minus 4. And I just want to quickly illustrate that geometrically. So I don't know if you're going to be able to see the font over here, but maybe I can blow it up or something like that and edit. I don't like editing, but let me make sure I'm recording with the correct microphone and that it's not muted. That's good. Here. So what I'm going to do is I'm just going to take this and drag it. Now, by default in Geogebra, when you drag something, it doesn't drag a line. It doesn't change the slope. So here's the original thing, and I'm going to just drag it up. So I don't think you can see, but all it's doing is changing the value on that right-hand side of the equation. Okay. So my claim is that it doesn't matter what two values we put over here. The fact that these lines are not parallel means that, so 6x plus 7y equals something. That describes one of these lines given, sort of by this one of these families of lines with this slope. And when we look at the columns perspective, it'll be a little bit more clear what's going on there. And the 3x plus 2y is equal to such and such. That describes one of the lines with these slopes. Now, what this means is that it doesn't matter what the such and such is on the right hand side of the equation. You know, you can move this really far out and this one really far out. You zoom out and you go over here, you can find the intersection point using the exact same procedure. Now, the question you should be asking is, what happens if these two lines are parallel? Okay, so what I'm going to do is change this from 3x to 21/6 y. Okay, and now the two lines are parallel. Now, what you can see is that we either have no solutions. If the two lines are parallel, like this, and they aren't the same line, then we have no solutions. And if they are the same line, then we have infinitely many solutions. So this is what is meant by the linear system or the matrix not being invertible. If the two lines are parallel, then either we can't solve it, or in the case where they're the same line, we can't solve it uniquely. Okay, what I'm going to try to convince you right now is that the two lines are parallel precisely when the determinant of the associated matrix is equal to 0. Now, this geometry picture of parallel versus unparallel versus not parallel, I think I've convinced you that this does not depend on the value on the right-hand side of the equation. In other words, when we write ax equals b, so this is a typical way that you think about it. This matrix is called A, this one is called x, and the vector is called b. Whether or not the system can be solved only depends on A. And what I'm going to try to do is convince you that it only depends on the determinant of A. Okay, so the reasoning pattern that I'm going to use depends on the value, on the coefficient associated with y being not equal to 0. So I'm going to first of all get rid of these crossed lines. And I'm just going to show you what happens when the coefficient on y is equal to 0. Well, then you get x is equal to something, which is a vertical line. Okay, so when you have two vertical lines, then you have x is equal to something and x is equal to something else. Obviously, this system is not invertible, i.e. it doesn't have a unique solution, meaning there isn't a single point of intersection. Now, let me show you, let me make a new MyPaint window. Okay, so if we have x is equal to something, foo, and y is equal to bar, and x is equal to bar. Well, then the system of linear equations, let's just say it is let me actually rewrite it as ax is equal to foo and cx is equal to bar. You're going to see why I'm doing this in a minute. So this is equivalent to the matrix A, C, 0, 0 times x, y is equal to foo, bar. Okay, and then obviously the determinant of this matrix is A times 0 minus 0 times C, so the determinant of A, 0, C, 0, this determinant is obviously equal to 0. Okay, so in the case where we have two vertical lines, the determinant is 0. Okay. This proof probably isn't logically tight, but there's a way to make it logically tight. I'm just trying to illustrate. Again, I'm not trying to give you a full singing, dancing, explain everything super thoroughly and from first principles, explanation of linear algebra. There's plenty of other playlists that do that. I am trying to untie knots that most people have in their head regarding this subject by just showing you what's going on. Okay, now if one of these is, so if one of the lines is vertical and the other one isn't, so I'm just going to make this x plus y is equal to 33, then we have a unique solution because the lines clearly aren't parallel because one's vertical and one isn't, so we have a unique solution. So I'm just going to pretend that it's this second equation. I'm just going to edit it in place, and I'm going to call this d. Well, in this case, the determinant is equal to a times d. Okay, and if a and d are not equal to 0, this is not equal to 0. So let me actually let me redo it. So if we have ax is equal to don't care, and cx plus dy is equal to don't care, then the determinant, then this is solvable, and we see that the determinant of a0 bd is equal to ad, which by assumption is not equal to 0. Okay. So now we're going to move to the case where we have two lines in the plane, both of which are not vertical. Okay, and this is a more general proof. So now assume both lines are not vertical. So we covered the case where both lines are vertical, in which case the determinant is 0, where only one of the lines is vertical and the other one isn't, in which case the determinant is not equal to 0. So now we're going to talk about both lines not being vertical. And the reason is that I want to be able to write the equation in slope-intercept form. So what I mean by this is ax plus by is equal to, and then cx plus dy is equal to, what should I call this? I'm going to call this, let's use Greek letters. This is alpha, no, that's a bad Greek letter. Yeah, let's just use Greek letters, alpha and beta, okay? So this system of equations is equivalent to, the first one is y is equal to minus a over b times x plus alpha over b. So all I did was moved the ax over and divided both sides by b, and also y is equal to, well, let's just do the same thing, minus c over d times x plus beta over d. Okay. Now, these two lines, so this is describing two lines, these are two lines in slope-intercept form. So let me use colors. This first line I'm going to call line 1, and the second line I'm calling L2. This is the second line, and this is the first line. Okay. Well, if you think about it for a second, line 1 is parallel to line 2 if and only if, or precisely when. I like the phrase precisely when. It means the same thing as if and only if. The slope, if they have the same slope, that is, the slope is the coefficient attached to x, so in this case it'd be minus a over b is equal to minus c over d. Well, if we rearrange this equation, let's cancel the minus signs, so a over b is equal to c over d. Okay, well, this is equivalent to AD minus BC equal to 0. So the system is invertible. So let me frame it this way. Has a unique solution, or actually, let's say not solvable uniquely, if and only if the two lines are parallel, if and only if this, if and only if this, if and only if this, and then this is of course equal to the determinant of the matrix A, B, C, D. Okay, so, and then the converse of this is that the equation, the system of equations can be solved uniquely can, affirmative, if and only if AD minus BC is not equal to 0, i.e. the determinant of A, B, C, D is not equal to 0. Okay? That's what it means by the matrix is invertible. It means the system of linear equations can be solved uniquely. Now this is just the 2x2 case. The 3x3 case is a little bit harder to see. So let me just briefly illustrate geometrically what's going on in the 3x3 case. So in the 3x3 case, you'll have ax plus by plus cz is equal to alpha, and then dx plus ey plus fz is equal to beta, and then gx plus hy plus iz is equal to gamma. Okay, and then the same thing actually is true here, but it's much harder to visualize the 3x3 determinant. I'm going to give you, in a couple videos, a really cool way to visualize the determinant, and maybe that'll convince you that there's something going on here. But what I want to do is explain try to port this logic about the two lines meeting, whether or not they meet, into a higher dimension, because there's a little bit more going on here. So I'm just going to call this P1, this is P2, and this is P3. Okay? So the first equation is describing a plane in three-dimensional space. So I'm going to try to draw it. Okay. The second equation is describing another plane. How should I draw this? And then I'm going to make it really small. Okay, and the point being that you take these two planes and they're going to meet in a line. So this is a very bad drawing. Let me start over. Let me just This is a much better drawing. Okay, and then the meat of these two planes is a line. Okay, and then this third one, I'm just going to take, so the set of points, the set of x, y, z, such that p1 and p2 are true, is, so let's call this blue plane, this is this is p1, and then this is p2, okay, and then this yellow is p1, the meat of p1 and p2, or the intersection of p1 and p2. Okay, let me draw this yellow line, and then what I'm going to do is draw the third plane as if it's just fake. Sorry. I'm getting much better at using the drawing program, though. And then this is P3. And where's yellow? And then this is going to meet, so the meat of the plane and the line, that's going to be a single point, which in other words is P1 intersect P2 intersect P3. Now there's a whole host of ways that this picture could go wrong. You know, if two of the planes are parallel, or if they're the same plane, maybe this line lies on the third plane or lies in a way that's disjoint. But generally, if you take three planes and you find the place where they intersect, it will be a single point. This is also the logic of, well, if you have three equations, or three unknowns, you need three equations, because, or the first two will describe a line, the third one will describe a plane, or will describe a point, right? So this is sort of the picture in general, is that each equation removes a dimension. So in the 2x2 case, we have two lines meeting. In the 3x3 case, we have three planes meeting. Okay, and then the condition that there is a unique point at which all three planes meet, that happens to be, where is white? The determinant of A, B, C, D, E, F, G, H, I. If this is not equal to 0, this is not equal to 0 precisely when the three planes meet in a single point. Now, I think this is a good place to stop. The next video I'm going to talk a bit about the columns perspective, and that should be good. And then I'm also going to want to explain this interpretation of the determinant as having something to do with area or volume, but we'll need a couple videos to get into that. Anyway, thank you.